So here we're going to show you how this Taylor polynomial can mimic these curves. So I've given you a curve of sine x, so there's a sine function there. And here's our Taylor polynomial. This is just with one term. Okay, so n equals 1. So you can see that near 0, it's nice fit, but once we get beyond 0, it just completely diverges away from the curve. Okay, so this is not that useful when we just use one term. But if I go up to n equals 3, okay, now I have a cubic function. This is my Taylor polynomial as a cubic function using the first two terms of that Taylor polynomial. And we can see that it fits a little bit better. The cubic polynomial will accommodate this curve now a little bit. But again, it diverges away once we kind of get away from the center there. But what we could do is, and this is a nice thing about an infinite series, we can just add one more anytime we want. So we can just add one more term. And there's the fifth degree. So, oh yeah, it's matching that curve nicely now. And is allowing for more bumps, which allows for us to accommodate all these waves in the sine function. And so if I add one more term to that, okay, it looks a little bit better. Add one more term, it looks a little bit better. Add one more term, it looks a little bit better. And as I add more terms, it fits better and better and better. And the nice thing about these infinite series is that there is no limit to how many terms we can add. We can just add one more. If we want it more accurate, we can just add one more, and one more, and one more, and one more. We can just keep on adding terms to this to get a more and more accurate polynomial approximation to this graph. And in fact, if we do this infinitely, it's not even an approximation. It is exactly equal to this graph of sine x.